slide. And what you see here is poker, a royal flush, and ink being dispersed. And that's because we're talking about the X factor in spontaneity. I already talked to you about the first factor. The first factor is energy. The second factor has to do with why ink will disperse when you put it in water, or why you never win in poker when you go to Las Vegas, okay? Or why the probability of winning is very low. So that's what we're talking about here. So a reminder that thermodynamics is a state function. All you need to know is the final point and the initial point. Unlike kinetics, where kinetics will depend on the path. How many steps do you have? Which is the transition state. So the kinetics of a reaction, the speed of the reaction depends on the path, whereas the energy of the reaction, all you need to know is the energy of the product, energy of the reactant. It doesn't matter how many steps you have in between. You're going to be able to calculate that energy. So kinetics is, kinetic domain is the path, whereas thermodynamic domain is a state function, okay? And that's what we're doing. So what are the common example of spontaneity? And you guys already know this in terms of spontaneity. When we age, I can't grow any younger. I can't get I can't turn my gray hair back to black, okay? It's just a process in which time sort of dominates. Objects falling, when you have an item and you let it go, it spontaneously drops. And it doesn't spontaneously float. So that's a spontaneous process. I already said that time it moves in the forward direction. Interesting, because I was just, in these days when I have to entertain myself, I go to YouTube and I look at some science footage, and I came across one very interesting one. I'll show it to you later. It talks about time and reality. I don't know if any of you have seen it, but I'll share it momentarily here because I thought that was pretty interesting. Sunrise, that's spontaneous. We could expect the sunrise to happen tomorrow and that the sun will set later on today. Okay, that's spontaneous. Ink mixing, I already talked to you guys about that. Chemistry exams, those are spontaneous, okay? But even though they're spontaneous, some of these can be made non-spontaneous depending on the conditions, okay? Like for example, chemistry exam. If you bribe me enough, I might cancel the exam, but that won't happen. But again, just like water freezing, you can make it non-spontaneous if you change the condition, okay? It depends on the condition. So those are what we mean by spontaneous and non-spontaneous. So we do grow old. Gas do not contract. We do not grow young. Gas do not contract. Water does not freeze at room temperature. Okay, 298. Time doesn't go backwards. And chemistry exams are not canceled generally. Okay, but depending on the conditions, we can get the water to freeze or the frozen water to melt. It depends on the conditions that you apply. So that means that these thermodynamic parameters can be made reversible if you change the conditions. What you guys will find out, however, is that there are certain things that are irreversible. It'll always be spontaneous. You can't change it. There are other things that are reversible. You can change it, and that depends on the conditions that you have. Okay, so let me just see. There's something in the chat here. Let me do this real quick. Water is a molecule. Molecules are never zero. Some elements, yes. Waters are molecules. It's got more than one atom, in other words. So the enthalpy or the thermodynamic parameters of water is not zero, okay? Because it's not found in its pure state. Pure state meaning its elemental state. Let's see, solid liquids are 0 degrees, water is not zero. Yeah, solids and liquid are zero in its elemental form. That's the thing. Let me see. Okay, so you just have to remember that if it's not in its elemental state, then its thermodynamics value uh, isn't zero. If it's not 1 atmosphere, if it's not 298, then it's not zero either. Those are the conditions that we're talking about. So I remember when I was in graduate school at Santa Barbara, Stephen Hawkins actually came in and did a seminar. So that was a few places that he visited when he was promoting his book, The History of Time. And it was pretty amazing, his seminar. It was a packed session. And even back then, back in the late 80s, mid to late 80s, it was very popular. But he gave us a seminar in which he talked about his book, The History of Time. And he gave us a scenario in which he said that, yeah, based on the expansion of the universe, this is based on the knowledge that they had back then. Since then, we've sort of tweaked it here and there. But when Hawkins was talking, he said that based on the expansion of the universe, time moves forward. But there may be a scenario in which the universe stops expanding, and then we get to the big crunch. And the big crunch is basically when, because of the gravitational field, because of the mass, the universe will start contracting. And he says, what would that universe be like? And he painted us a picture is that, well, maybe instead of time moving forward in the big crunch, time will reverse itself. What will happen is that we rise, we are born from our grave, and we go from an old crickety person to a newborn, and we die in the wombs of our mom. When milk is spilled, it self-assemble into our glass. So he was painting these weird scenarios in which everything's moving backwards, and you gotta sort of like follow along with his story. And then he goes on to say that, well, that might be great to see in a science fiction movie, but it will never happen based on the mathematics, because as you guys know, math is like the universal language. It explains a lot of things. And he says that based on a singularity theorem, you get to a singularity where that you get an undefined equation. It's like dividing something by zero. It's undefined. You don't get a solution. And so anyway, he built up this thing, and then he just destroyed it based on a simple statement like that. So it goes to show you that even thermodynamics has its place in thinking about the universe and all that. And yes.
Does that mean time travel is never possible?
I don't know about that. This is a good time to actually break out from this session and share with you this video that I was watching the other day. So let me share my screen here. And
because on the topic of Stephen Hawking, didn't he host a party and then put out the invite the next day to see if anyone would come?
Yes, he did that. Actually, he tried to put out the invite to see whether or not people in the future would come to his party of the present. So yeah, he did that, and he showed that time travel wasn't possible, at least based on his experiment. If you guys have time, this is a 30-minute clip, and there's actually a second part to this, so it won't take that much. Plus, it's pretty entertaining science. They talk about time and how time is not linear. It actually is spontaneous all around us. What we do in the future influences our past, and what we do in our past influences our future. So that was totally radical. That was totally mind-boggling based on my limited brain, but that's what these scientists are proposing. Anyway, you guys can watch it and see what you can get out of it. I always like to present these things because what we find out, it's just like back in the 1900s, we didn't really know about atoms, but as we investigated further, we started to define the parts of the atoms and then give us better idea of how atoms work. Well, what we're doing now is defining subatomic particles. And maybe in 100 years in your lifetime, they'll get a better idea of what exactly unifies these theories together. But anyway, it's always good to hear what other people are working. Other people much more smarter than me are working on. So let me go ahead and continue here. Okay. Now you have an idea in terms of what we mean by spontaneity, I hope, based on our knowledge now. I've got to qualify that because it may change tomorrow. Science is always evolving. So we talked about this already. This is Hawkins, of course, and he just died. Was it a year or a couple of years ago? So spontaneous does not equal rate. It does just because something's spontaneous, that doesn't mean it's fast. It just means that it proceeds in that direction. Okay. We know that when something is dropped, it's spontaneous. It goes from a high state to a low state. If you take your pen, for example, hold it arm's length and then let it go, it'll drop to the floor or drop to an item when it hits. Okay, that's spontaneous. When we take sodium hydroxide and we put it in water, it spontaneously goes into solution and energy is released. That's an exothermic reaction. But yet, when we take ammonium chloride, that's the chemical that I told you about in these ice packs, and you break it, it too spontaneously dissolves. And yet, because it gets colder, that's an endothermic process. So the question is, well, one releases heat, and that makes sense that that's spontaneous because when we drop things, that's a spontaneous process. On the other hand, we can't take our mouse and expect it to leviate, okay? It doesn't just automatically rise up. You can't go from one floor to another spontaneously. You need an input of energy. Well, the key here is that enthalpy, energetics alone is not the answer. What you need to do is look at the second law of thermodynamics. And the second law of thermodynamics simply states that when a system becomes more chaotic, more disordered, then it's said to be a state at higher entropy, and entropy is a spontaneous process. The second law of thermodynamics simply states that the entropy, the chaos in this universe is not constant, it's ever increasing. And all you gotta do is look in my office, in my room, it's just a mess. I've got things everywhere. It's just, entropy has taken over my life, basically, okay? And if you take a look at an ink, which is highly ordered, and you put it in water, it disperses. That's because entropy is taking over. So that's an example of entropy. And entropy was actually defined by Ludwig Boltzmann. This is the same guy that gave us the Maxwell-Boltzmann distribution plot, okay? But he's a Russian, and he defined entropy as a thermodynamic state function, and it has to do with the number of energetically equivalent ways to arrange a component. Yeah, that's a little bit abstract for us, so let me try and explain that in more simplistic term. First of all, this is the equation he derived, that the entropy is equal to K, a constant, which is the gas law divided by Avogadro's number, times the natural log of W. And W is what we're going to be looking at, microstates. So you got to buy into this microstates before you can appreciate entropy, okay? So what are microstates? Well, let me try and explain it to you through a card game. Or chaos, okay? So like I said, entropy is always overtaking us. Entropy is always increasing, unlike energy, in which energy is constant. Entropy is not constant. It continues to get bigger. So the question is, if entropy is always increasing, why find it? Why fight the disorganization in my room or the disorganization in my checkbook or things like that, okay? Those are the things that you could ask yourself about entropy. It's not conserved. Entropy, like I said, describes something called microstates or states. So let's go back to this card game. If you've ever played poker, even if you haven't played poker, the highest winning hand is a royal flush. A royal flush is where you have the highest um, cards with the same suit. Uh, Ace, king, queen, jack, 10, either in hearts, spades, diamonds, or clubs. And that would be um, the, the hand that wins everything. But when you're dealt 5 cards, there's a chance of only 4 out of 1,302,544 possibilities. That's the number of ways you can arrange 5 cards. 1,302,544. That's very, very low probability. Not an impossibility, but very low probability. Okay? So the chance of you getting nothing other than a royal flush happens to be 1,302,540 possibilities. That's why your chances of not winning is greater than the chances of winning, especially with a royal flush, because there's a higher ways of arranging nothing compared to a royal flush. Okay, so there are greater probabilities of getting nothing rather than something, and natures prefer to take on the path of highest occurrence. That's entropy in a nutshell. Nature prefers you get nothing, okay, or at least more chaos. So let me try and explain that through chemical reactions. Let's say we have 2 chambers connected by a tube, and I have 4 gas particles to make this particular concept more simplistic. If I put all the gas particles to one side, then that's one arrangement. If I put only one of the particles on the other side, then I have 4 ways of doing that. That's more states than the other. Now, if I put 2 particles on the other side, then there's more arrangement. See how we're talking about microstates here? And that the microstates, when the 2 gas are even in both sides, are higher than if the gas or the particles are on one side. And again, this thing of entropy has to do with microstates. So the fact that randomness, where both gases are scattered between the 2 sides, has a greater probability of occurrence, that means higher entropy. So entropy has to do with microstates and the probability that it'll happen. It's not to say that all the gas won't just collect on one side. That's a possibility, but highly improbable, okay? It's not impossible, just highly improbable. The most probable state is when the 2 gas mixes, especially if you have more than 4 particles. If you have a high quantity of particles, a mole of particles, then the probability goes up even further. So that's what we mean by entropy. Entropy is the microstates that we have. And again, like I said, although not impossible, it's highly improbable for it to be highly ordered in order for all the gases to stay in one chamber and leave one other chamber empty. Okay? That's entropy for you. Entropy states that one of these microstates are possible or has some probability of occurrence. So the more states available, the greater the entropy. So the question really goes back to, why does ammonium chloride is spontaneous? Why is it when you crack that seal, it spontaneously dissolves? And that's because when it dissolves, it's a much more chaotic state. There's more greater probability of that occurrence than in its isolated form. Okay, so even though it's endothermic, entropy plays a role in making that particular process spontaneous. So when we look at spontaneity, we have to weigh the energetics with the chaos. If the chaos outweighs the energetic, it'll be spontaneous. If the energetics outweigh the chaos, then depending on whether it's exothermic or endothermic, then that reaction will not occur. So you have to weigh the two. And we have a very nice equation in which you guys can do that. Okay. So like I said, the ways to the microstates available in a solid where everything's linear, where everything's orderly, you have less microstates than in the liquid form. The liquid state has these particles moving from one place to the other. There's more microstates available. That's why the liquid has a greater entropy than the solid. And then in the gas state, there's even greater degrees of freedom. These things can move in a three-dimensional volume, and they could be tumbling amongst each other. So the entropy of a gas is so much, much more greater than the entropy of a liquid. And that's what we see. The solid has a certain entropy if it's not under standard state. In fact, the only time the entropy could be zero truly is through the third law of thermodynamics. Pure crystalline solid at 0 Kelvin has an entropy of 0. Okay. Then it goes, but if you have a solid that has a low entropy, because it's an ordered state, less microstate, a liquid has more microstate, it has a greater entropy, and then a gas has even greater entropy. So you guys know about Charles' law. Charles' law says that if you take a substance, a gas, and you cool it, then if you could extrapolate it so that you keep it in its gas state, then you get to a point where the gas stops moving. And when he did this experiment and he extrapolated to a temperature, he found out that there was a limit to the temperature. And that temperature was minus 273 degrees Celsius. We call that, of course, absolute zero or 0 Kelvin. So unlike elevation, unlike enthalpy, entropy is an absolute scale. We do have a 0 point where everything could have 0 entropy, and then it just goes up from there. So entropy, thermodynamic value, is not relative. It has an absolute scale. Okay. And the third law of thermodynamics simply states at absolute 0, the entropy of a crystalline solid of a pure substance is 0. So that the main thing in terms of spontaneity is the second law of thermodynamics. Second law of thermodynamics tells us that if the spontaneity is defined by the entropy of the universe getting larger, okay? That's how we define spontaneity. Entropy of the universe is always increasing. It's not conserved. The entropy of the universe is defined as the entropy of the system plus the entropy of the surrounding. Predict whether a process is spontaneous or not. It's positive. It's spontaneous. If it's 0, then it's at equilibrium. Okay? If the entropy is negative, it gets more organized. Then the opposite event is the spontaneous process. Okay? So most probable microstate is the one that is more random, is the one with greater entropy. So it goes back to this question. So why does your room eventually, well, why does my office eventually clean up if the entropy of the universe is always increasing? Why should I find it? Well, if it does get organized, maybe during the summer, it's because I pay the price. My entropy gets worse because I have to put in the energy to organize it. So my room would be the surroundings, I would be the system. The entropy of the room would go down, but the entropy of me would go up. That's basically how we would define the universe. So that's how we do not disobey the second law of thermodynamics. Entropy of the universe is always increasing, and my surroundings gets lowered at the expense of me going up. Okay, so this is basically the equation that you can write down. The entropy of the system is going to go down negative, but the entropy of the surroundings, that's me, will pay the price. So the result of the entropy is always increasing. So let's take a look at this. This will be the last topic that I talk about, okay? And this will take us at the end of the class. And this will also help you with the activity that you guys have in thermodynamics, which is scheduled for next week. Predict which system has the greater entropy. Copper. Uh, is the entropy lower at 273, 295, 298? You guys know the entropy of copper metal is going to be greater at 298 because it's at a higher temperature. The entropy is a temperature function. At higher temperature, the molecules are going to be moving faster. There's more available state when the chemicals have more energy, and that's what you see if you look up the entropy values at these particular temperature. It's 31 joules per mole Kelvin. Notice that entropy is joules, okay? Enthalpy, that's delta H, is kilojoules. So when you mix both of these parameters, you got to make sure that the units are the same. That's a common mistake I see, okay? Let's move on. Sodium. Which one would have the greater entropy? Well, you guys should know it's going to be gas. And that's what we see. The entropy of a solid is 51. Entropy of the gas for sodium is 153.6 joules. How about water? Well, that's again, the gas form would be the higher entropy. And that's what you see. 69.9 for the liquid, 188.7. So this is a no-brainer. The higher entropy generally are higher temperatures or in the gas phase, which is a more chaotic state. And that's what you see with carbon as well. Carbon at 273, graphite is 5.7. Remember, it's positive, even though it's at 298 because it's entropy. The only time it's zero is at 273 minus 273 Kelvin, absolute zero. So it's not zero here. In this particular case, it's 158 at 298 Kelvin. So let's take a look at more complex system. Let's take a look at sodium chloride. Sodium chloride crystalline solid versus dissolve. Well, in the dissolved form, it can move around, the ions can. So what happens is that the entropy goes up. And so again, that's a no-brainer. But take a look at the next one, aluminum chloride. Look at the two entropy values. It's 166, and remember, this is relative. You're calculating the before and after. That's why it's a negative. It gets more organized here. So we have 167 in its solid form, but it gets more organized in its aqueous form. Where does the entropy go down? And the reason why the entropy is negative here is because when you take aluminum chloride and you put it in water, the aluminum chloride has to break apart. And remember that aluminum is +3. That's the kicker here. Because it's +3, it's going to demand that the water molecules be more highly organized around the aluminum ions. And because of that organization, you're going to have fewer microstates. That's why the entropy decreases for that versus the solid form, okay? Because of the +3 charge on aluminum. That's the key. Let's take a look at methanol. Methanol, the aqueous form is a little bit higher than the liquid form. That's because methanol can hydrogen bond with water, but the entropy is not that much higher than its liquid form, okay? Let's take a look at oxygen gas. Certainly, the liquid and the gas form is going to be, or the gas form is going to be a higher entropy than the aqueous form. In the aqueous form, it's dissolved in water. But in the gas form, it's going to be free to move about randomly. So it has more degrees of freedom in the gas form than in the aqueous form. That's why the entropy for oxygen gas is 205 versus dissolve 110. Let's take a look at the diffusion of these gas. Actually, it's going to be greater than 0. The other way to look at entropy, we already know at higher temperature entropy increase. We know that the gas has a higher entropy than the liquid or the solid, but also complexity. The more complex a chemical is, the more subatomic particles, the more ways these subatomic particles can arrange each other, and so the greater the entropy. That's why if you look at the elements, lithium, sodium, potassium, and rubidium, let's say they're all at the same temperature. Let's say they're all solid. the entropy of rubidium is higher because um, it's got more subatomic particles. There's more ways of arranging those subatomic particles. Could you describe why the solid has a higher entropy for aluminum chloride again? Aluminum chloride has a +3 aluminum charge, and the +3 makes it dictate how the chlorides are going to be arranged. But when you dissolve it, the aluminum and the chloride separates, okay, to their ions. But there's still a +3 ion there. The +3 of aluminum dictates that's a very high charge. It dictates the orientation, the specific orientation of the water molecules. And that specific orientation is going to be more ordered, highly more ordered than the aluminum chloride solid. That's why the entropy is lower in the aqueous form versus the solid form. It's because of the +3. So when you go into your activity next week and you're asked to figure out whether the entropy is higher or lower, when things dissolve, you got to take a look at the charge of the ions. The higher the charge, when it goes into the water, the lower the entropy, because it's going to dictate that the hydration process be more ordered. So hopefully that explains things. So when this last part, complexity of the element, it doesn't even have to be an element. It could be like system. Which one has a greater entropy? A butterfly, your pet cat, or chimpanzee? Just based on the structure and the intelligence and all that, you're going to see the one with the greatest entropy is going to be the more complex one, the chimpanzee, followed by the cat, followed by the butterfly. Okay, so complexity, based on the complexity, the higher the entropy. And you can calculate these entropy values based on the thermodynamic parameters that you can find in your textbook. And remember, it's always the sum of the products. Most times the thermodynamic parameters products minus the most times the thermodynamic parameters reactants. So we can do this for enthalpy, we can do it for entropy, we can also do it for something called free energy, which is what we will talk about next time. So here's the last example. What's the thermodynamic parameter entropy for beryllium hydroxide going to beryllium oxide and water? Look at that reaction. And just based on the top of your head, would you say that the entropy is positive or negative or zero? And look at the phases and look at the number of particles. You could say that the product is more random than the reactant because you have two, so you're breaking it apart to many. So just based on no calculation, you would be able to say that the entropy is increasing. The entropy should be positive. No calculation. Let's do the calculation real quick. The values for water is 188.83 joules. Beryllium oxide is 13.77, and beryllium hydroxide is 50.21. So if we do products minus reactant, we actually will get a value of positive 152.39 joules per mole Kelvin. So if you predicted that the entropy would increase because one, you've got a product in the gas state, and two, you've got more particles in the product than the reactant, then you would be right. So you can predict the increase or decrease of entropy if you look at a reaction, if you use your common sense. Okay, so that takes care of this particular discussion. Next time, what we will do is we will take entropy and enthalpy and put them together.